Chapter 6, Section 4. This video lecture is an introduction to energy. Our learning outcomes today are: explain the nature of energy. We want to understand what exactly energy is, and we want to understand how energy is governed by the laws of thermodynamics. And these are really important to understand how life uses energy. For hundreds of years, scientists and naturalists and people in general have always wondered, what is the secret to life? What makes a bird like this green heron inherently different from a rock? People have known that life is different from inanimate objects, and we discovered in the 1800s that energy might be part of that. In the 1800s, scientists discovered electricity. They may have discovered it a little bit before that, but it was in the 1800s when they started experimenting with electricity. They started experimenting on electricity with dead animals. And one of the things they would do is apply a little bit of an electric current to a dead frog, and it would move. And they're like, energy must be really important for living organisms. In fact, in the 1800s, Mary Shelley wrote a book called Frankenstein. You may have heard of that. And in our modern day depictions of Frankenstein and him creating his monster, it's the idea of some mad scientist taking a corpse, and there's always some lightning or electricity involved. Well, that's not far from the truth. Energy is incredibly important for living organisms. We can't exist without a constant input of energy. However, bringing something back from the dead is impossible, and that's governed by the laws of thermodynamics that we'll talk more about later. So the question becomes, well, what exactly is energy? Perhaps the easiest way to think about it and to define energy is the ability to do work. And well, what is work? Simply, the first definition of work was weight lifted over some distance. So here I am bench pressing. I'm lifting some weight over a distance. I'm doing work, and that requires energy. Another way to think of work and energy is you're causing change to the universe. It's a much broader definition here. So causing change to the universe, you're moving something, you're building something, you're using energy to break down another molecule, you're cleaning your room, cleaning the kitchen, all of these things that aren't so fun. You're causing change to the universe by doing work, and work requires energy. In 1905, a young patent clerk named Albert Einstein revolutionized the way we understand energy. He came up with this little equation, you may have heard of it, E equals mc squared. That is, energy is equivalent to mass times the velocity of light squared. And that is a lot of energy tied up in matter. Let me explain you. What Einstein showed with his famous equation is that there is a lot of energy tied up in matter. So if we take the speed of light, that's about 300,000 kilometers per second. That's fast enough to go around the Earth about 7.5 times in 1 second. So the speed of light is really fast. Now if I take energy, something that weighs a gram, like a dime, they weigh about a gram, and I can multiply that 1 gram times 300,000 kilometers per second squared, we can start to understand how much energy is tied up in matter. Let's continue. Next, we're going to convert 300,000 kilometers per second into scientific notation so it gets easier to work with. We'll do a little metric conversion. We'll convert kilometers to meters. There's about 1,000 meters in a kilometer. That's why that number 8 goes up from 5 to 8. And then we're going to square it. That's going to give us a big number. 1 gram times 9 times 10 to the 16th meters squared over seconds squared. Now, if you're familiar with some physics, 1 joule is equal to 1 kilogram per meter per second squared. So, what that means is, if I have 1 gram of energy, there would be approximately 9 times 10 to the 13 joules. That is 90 trillion joules of energy. We can convert that to kilocalories. It would come out to be about 21.5 trillion kilocalories. That's such a large number that most of us can't even comprehend it, but we can comprehend this. Einstein's simple equation, E equals mc squared. It revolutionized the world and brought in the atomic age because we realized that there's an enormous amount of energy tied up in mass. And in fact, whenever we've blown up these very powerful nuclear weapons, about 1 gram of matter is converted to pure energy, and that's enough to create an atomic weapon. It's an incredible amount of energy. Well, energy is governed by the laws of thermodynamics. There are actually four laws of thermodynamics, and we're going to talk about two of them. And no matter where you're at in the universe, the laws of thermodynamics are going to apply to all systems. So, what exactly is a system? It's basically a set of components that are interacting but are within a boundary. So, here's a simple system. You can see there's a boundary and everything in there is interacting. Some systems are closed. For example, the universe is a closed system. What that means is nothing gets in and nothing gets out. So there's a boundary, and everything that's going to happen within the universe occurs within that boundary. So this would be an example of a closed system. Unlike the universe, life, or a living organism, is an open system. In this case, there's still a boundary, but energy and matter can enter the system. And remember, we're getting energy in and matter in, and things can exit as well. Let's take this fish right here. This is a South American leaf fish, and we're going to get energy and matter is going to enter in through its mouth, and then energy is going to leave as heat, and matter will be out as the feces leave it. Because life is an open system, it's like the force. Energy is always flowing through life. You cut life off from energy, and eventually that living organism will die as it slowly goes toward equilibrium and decays into much simpler things like carbon dioxide and a few minerals. An important point to remember is that the laws of thermodynamics apply to all systems. That includes life and the universe as a whole. Now, there are two laws of thermodynamics we need to know. We've already covered them. The first law of thermodynamics: energy cannot be created nor destroyed, but you can transfer it and you can transform it. But anywhere you go in the universe, we're not creating or destroying energy. That's pretty nice. It's also called the conservation of energy. You know, that first law of thermodynamics said, we're not creating or destroying any energy. Does that sound too good to be true with you? That the universe is not losing any energy? Well, if it is too good to be true, that's correct. And that's because there's the second law of thermodynamics. And it says, every time energy is used, the amount of energy that can be used to do work decreases. So what that means is not all energy is created equal. Some is better used for work, like the energy stored in chemical bonds, but other forms of energy, like thermal energy and heat, well, that's not very good for doing any work. And the reason why is because of this thing called entropy. And every time we use energy, we transfer it or transform it, entropy increases. So what is entropy? Entropy is a measure of disorder. So what that means is, if you've got entropy, look at this words right here. Imagine all these dots coming together to form that E. That would be highly ordered, like a cell would be highly ordered. Well, as you become more and more disordered, entropy increases. So a living organism would be very low entropy. The air in your room would be very high entropy. There are several consequences to entropy constantly increasing in the universe. Remember, the universe is a closed system, so there's not gaining any new energy. We're not destroying it, but entropy is always increasing as the universe goes toward equilibrium. That's not a good thing. And about 1 trillion years or so, the last star will wink out of existence and the universe will just be a cold, dark place. But for our purposes right here today, let's talk about, well, Frankenstein, or Frankenstein's monster. It turns out that a bolt of electricity will never reanimate a corpse. And the reason why is because of entropy. Entropy is a measured disorder. All the information that's stored in you begins to decay rapidly once you die. It's like burning a newspaper. All the information that's written on the pages of the newspaper are gone once it goes up in flame. You can never, ever recover that. There's another really good consequence of entropy that I like to think about. And that is, I will never have to face the zombie apocalypse. Because once something is gone, zombies can't exist. And we can thank the second law of thermodynamics, the fact that entropy is always increasing, that we will never be run down by zombies. Back to something a little more serious here. Don't forget, the laws of thermodynamics apply to all systems. That means life does not violate the laws of thermodynamics. Even though life is a very ordered system, very low entropy compared to the surroundings, that's because it's an open system. Energy is constantly flowing through organisms. You eat pizza on the weekend. Well, you get potential energy coming through you, and that energy will exit you as heat. You cut us off from our food supply or our energy supply, and eventually life will die. Life needs energy, and almost every living organism gets their energy from the sun, either directly or indirectly. We can thank ancient cyanobacteria that evolved the ability to do photosynthesis. That's where you take some carbon dioxide and some water and the energy in sunlight, and you create carbohydrates. So you kind of store energy in those carbs. And then you can break down those carbohydrates in a process called cellular respiration. That's how you and I get our energy, indirectly from the sun via plants. What that means also is that every carbon in your body also was fixed by a plant in photosynthesis.